We're going to be looking today at exponentials. And immediately there is an interesting problem, and that is, the question is, do we first do the calculus with e to the x and then consider its inverse, natural log x? That is one time-honored way to do it. And the advantage that it has is that the e to the x just seems friendly. And students like this, but the disadvantage is that it's conceptually messy. And you're going to see that as we walk through some of our proofs. I'm going to have to do some hand waving at a couple of points and just say, trust me, this works. And that's not really good proof technique. The other thing that you can do is to start with ln x and then go to e to the x. You can actually develop the calculus of the natural log first and then treat e to the x as its inverse. And the advantage of this is that it's conceptually clean. Someday in the future, I'm going to do a day where we just do this so you can see how that approach would go. But the disadvantage is that you need intervals first. Because what you do when you start with e to the x is you're going to begin by defining e to the x equals the limit as n goes to infinity of 1 plus x over n to the n power. And all that is needed for that is some limit machinery, and then you're good to go. But if you do this, then you end up defining the natural log of x is the integral from 1 to x of 1 over t dt. And of course that requires the whole machinery involving fundamental theorem calculus and definite integrals and all that. So we're going to do this because this is kind of where we are in life, but my heart lies with the second approach. Well, let's get right to it. E is one of the many things that is named after Euler. It is called Euler's number. And it arose from, of all things, a question of banking. If we have money, P, we're going to call that the principal. And we're going to invest that at a rate R. Then what happens is that if I have so-called simple interest, which is the easiest way to think about it, then at the end of 1 year, that interest is applied to the money so that in addition to the money that I already had, what I get is the interest rate, expressed as a decimal, times the principal, added to my balance. So if I start with $100 and I invest at 6%, which hardly anybody can find anymore, then at the end of the year I will have that $100 plus I will have 6% of 100, or I'll have $106. Well, you are sharp and with it, and so you can see that factoring out P gives us this expression 1 plus R to P. And if I now do this a second time, so this is year 0, this is year 1. If I do this a second time, then I will get all of the money that I had at the end of year 1, plus the interest rate times that. And at first it looks like this is going to spiral out of control algebraically, but then we realize I've got a common factor of 1 plus R to the P. And when I factor out that common factor, lo and behold, I have 1 plus R times that common factor. So that at the end of year 2, I'm going to have the principal times 1 plus R squared. Well, we can see patterns when we see them. And we can see that at the end of year n, we're going to have P times 1 plus R to the n. Well, this is nice scratch work, but we'd like to clean it up into concise mathematical notation, so let's do it like this. Let's say that the amount at and actually let's call this year t rather than year n, because t is for time. So the amount for the interest rate R at time t is equal to principal times 1 plus R to the time t. The trick, though, is that this application of interest happens at the end of the year so that my domain is only integers. In other words, I can talk about year 1, year 2, year 3, but if it's year 2.5, then I would only get the interest for year 2. In other words, I need to use some kind of int function to find what happens at the non-end years. Okay. Well, people are not always happy. Have you ever heard the phrase substantial penalty for early withdrawal in terms of investments? Do you pay attention to investments at all? Yeah. Well, what happens is, if you go into the bank and you say, I'd like to get a certificate of deposit, which is slightly better than a savings account, then the certificate of deposit will say substantial penalty for early withdrawal. And what they mean by that is, if you take your money out early, if it's a 5-year certificate of deposit, you take your money out in year 4, they are going to take back some of the interest that they had planned on paying. And people don't always like that fact. So what they sometimes want to do is to have investments where the interest is applied several times a year rather than at the end of the year. And we call that compound interest. So the difference between compound interest and simple interest is, for simple interest, we have the entire R applied on December 31st. And actually, this is all recorded, so if you do need to go back and take a second look at it, you can do that. Okay? Now, with compound interest, we're going to divide up the interest into little chunks, R over N, and we're going to apply that in times per year. So in the end, I get the entire interest, but I get it doled out in pieces instead of once a year. And that actually makes a difference in the amount of money that I get back. Because if you take a look, if you think about each slice, each nth of a year as being one little time piece, then you can see for year 0, we have P. For year 1, what's going to happen is that we are going to take our P and we are going to apply the interest rate, R over N, in times during that year. So that what you end up with is actually interest on the interest during that year. And the result is that your yield is slightly higher than it would have been if we just did simple interest. And at the end of year 2, what you end up with is P times 1 plus R over N to the N squared, or to the 2N, and so on. So that if I go all the way out to year T, I now end up with, let's express it like this: the amount for interest rate R applied in times per year at time T is equal to P times 1 plus R over N to the N T. Is everybody with me on the development so far? And common applications are what we call quarterly interest. So quarterly is where N is equal to 4, and we're applying it every 3 months. Monthly is common, N is equal 12, and banks that have really liquid accounts do daily. By liquid, I mean you can walk in and take your money out at any time and not pay a penalty for that. So daily would be n equals 365.25. Banks are very particular. Now when you get into daily, Euler starts asking this question. What if we went all the way and said infinitely fast? We would call that continuous compounding, where the interest is accruing instantaneously. In that case, you would end up with n going to infinity. And so the question now is, what happens to your effective interest rate at that point? The way that you calculate the effective interest rate is that R effective is going to be equal to 1 plus R over n to the n power. This is the amount that is equivalent to a simple interest applied once at the end of each year. So just to give you a sense of some of these numbers, if the interest rate is equal to 0.06 or 6%, and we are doing monthly compounding, then the effective rate is equal to 1 plus R over n to the n equals 1 plus 0.06 over 12 to the 12th power. And when you actually compute that, well, I don't think my poor calculator is going to handle it here very well. Please compute it for me. Oh, God. Yeah, I get 1.0617, and I need to subtract 1 from this. Here we go. So the effect of compounding 6% interest 12 times a year is that I get an effective rate of 6.17%. And that's called, in bank terminology, we call that the effective APY. Annual percentage yield.
What is there?
The -1. Yeah, sorry, let me write this properly. I needed a -1 here that I forgot about. Better? The effective rate is the equivalent simple interest rate that you would use to get the same yield. So if I invest at 6% compounded monthly, that is equivalent to investing at 6.17% simple interest. So the two are equivalent. So Euler now asks the question: what if we go all the way and we get a continuous rate? And to make it simple, Euler is going to pose it in terms of a problem. Invest at 100%. And of course, he recognizes it's absurd, but it makes the math easy. Compounded continuously. And so what he'd like is, what's the multiplier on that? And so you can see that if our quantity here is going to be like this, -1 if you want the rate, then he's going to take R is equal to exactly 1, and he's going to let n go to infinity. And so this is Euler's answer to this question. But now the question is, what's that limit? Because you could argue it in one of several ways. You could argue that as n goes to infinity, I'm raising something that is not exactly 0 to the infinity power, and so boom, I get infinite money. Must be nice. Or you could argue, well, no, as n goes to infinity, this is actually 0, so I'm raising 1 to an infinite power, and that's going to give me 1, because 1 times itself, any number of times, is simply 1. Interestingly, the answer is neither of those, because n is going to infinity at the same time that this is going to 0, and that sets up a race between the two quantities. Kind of like our limit as n goes to infinity of rational functions, right? There's a race between the numerator and denominator. And here, that race turns out to be a very, very interesting number. 2.71828, 1828, and then I believe the next two digits are 3 or 4 something. I'm not exactly sure. Somebody could actually punch in E into the calculator. Yeah. And so this is called Euler's number. It is possible to prove, and I believe Euler himself proved, that this limit right here must be bounded below 3. And it must be bounded above 1. But I don't remember if it was Euler that proved that or if it was somebody else who came along later. But in any event, Euler discovered this. So now he sets about to doing algebra and calculus with it. So I want to consider the algebra first, and we'll come back and do some calculus. With regard to the algebra, the first thing that Euler discovers is that he can pull off a clever substitution to rewrite this limit. And I'd like for all of you to do that. Let z equal 1 over n. And what I'd like for you to do now is to take this substitution right here and rewrite E in terms of z. E equals the limit as z goes to what of what? Go. Yes, sir. Why isn't it then? That's true. But it's going to 0 at the same time that that's going to infinity. So there's now a race between the two. There's a race as 1 over n heads towards 0 but is not 0. And the exponent goes towards infinity but of course is not infinity. Okay? So the limit as z goes to what? Well,
like you can just plug in the
0. As z goes to 0, that's right. To determine what z is going to, you let n go to infinity and ask what is z headed towards. You seem dubious on that. Does that make sense? Yeah, okay. And then now we go through and we substitute. What am I substituting? 1 plus z to the 1 over z. And this is going to be our second form for E. And it's extraordinarily useful at different points. So now that Euler had answered the simple question, we want to come back and tackle the slightly harder question. What if I'm investing at R instead of at 100%? Because nobody gets 100% interest, right? If you're taking 100% interest, you're like a loan shark or something. All right? So what about compound interest? At R% or at R. So we take the limit now as n goes to infinity of 1 plus r over n to the n power. And at first it looks like this is going to be impossible because we have that r buried. But we're going to be very clever and we're going to pull off a substitution. We're going to let z equal r over n, this quantity exactly right here. And so if we let z equal r over n, then our limit transforms into the limit as z goes to what? Somebody besides me. Zero. Exactly. Let it go to infinity and you see it. Keep going.
Oh, so 1 plus 3.
But to what power? Philip. We're going through and we're trying to substitute everything, and we've accomplished substituting everything except for n. What is n equal to? Bingo. Exactly so. And now we can see the advantage of our second form because I can rewrite this in terms of the power rule for limits. Except that's not n, that's r. I can rewrite it correctly in terms of the power rule for limits. And what is this quantity on the inside equal to? E. So that we get this remarkable result, the result of compounding continually at the rate r is that your multiplier is e to the r. So that I can now say that the amount for r at infinity of t is equal to principal times e to the rt, or the formula I commonly call PERT. Did you guys learn something like this in trig way back when? Big continuous compounding, you know, for p e to the rt. But at that time it was just like poof because. And now here you can see a little bit of the algebra behind it. We're going to get this exact same result in a very different way when we do consider differential equations. Questions so far? This is our setup. We haven't done any real algebra yet, but we're about to. Okay? Fair enough. First thing I want to consider is the algebra of exponentials. And that consists really of 3 properties, and we'll add one more tomorrow. And they are properties that you know and love. I can simplify the sum, difference, and product rules. E to a sum, E to a difference, and E to a product. And you guys actually know all of these already. What are they? E to the x plus y is equal to what? Everything. E to the x plus y is? And E to the x minus y is? And E to the x times y? Or? Yeah, that's right. There's a delightful little symmetry there so that I can do whichever I need. Interestingly, the proof relies actually on the exponent properties for integers, or not integers, rather, for generalized exponentials. And here's where our first hand waving is going to happen. If I take the left-hand side and write it in terms of my z form, the limit as z goes to 0, of 1 plus z to the x plus y over z, just like that. Then it's clear that that is the limit as z goes to 0 of x blah 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 to the x over z equals y over z, just distributing here. And then appealing to the exponential property that we already have, this like so, and now use the product rule for limits. Now it's z. Now each of these quantities here is equal to e to the x and e to the y respectively. So algebraically that makes sense to us, but notice that I pulled a fast one right here. How did I get from here to there? Well, I appealed to the sum rule property of exponents for the generalized exponential. How did I know that that's true? Well, I can prove it for integer values of the base. If I have 2 to the 5 plus 3, then that's clearly 2 times 2 times 2 5 times 2 times 2 times 2 3 times, and so you can add the exponents. But what if I'm not dealing with an integer exponent, for example? What if my exponent here is pi? What does it even mean to multiply something times itself pi times? So here is the first place where I kind of have to cheat in my development here. And I don't like it, because conceptually it's messy. The other two proofs are very, very similar. I'm not going to bore you with them. And so I want to get on to the calculus. Unless you have questions. Well, I didn't say that. I said that. All right. So now let's consider the calculus of exponentials. So the first thing is this formula is the definition, but it turns out that computationally it's a real problem. And to get that, what I'd like for you to do is to, everybody take your graphing calculator, and I'd like for you to pick a large, and by large I mean 10 to the something power, the value of n, and estimate this limit with a large value of n. Go. Do that at this time. And then I'll play along too, get my calculator. And when I happen to use 10 million, I get an estimate for E that's not too bad. Compared to the actual retail value, which is listed by the calculator, so in 4 places it's great. What value of n did you use, Stephen?
I got it.
Okay. How many 9s are we talking about?
I did 12.
Okay.
So I got.
So we're going to write that as, it was 12?
Yeah.
So we'll write that as 1 times 10 to the 12 minus 1. Okay? And when you did, you got E is about what?
So first, add an extra and then 1.
You got 1. Let's try that again. So you have 1 plus 1 over, let's just make it 10 to the 12. That's what is 1? 1 E 12 to the 1 E 12. Let's not do that. Okay. In fact, that's spot on to however many decimal places. What did you what end did you use?
10 to the 9.
10 to the 9. How'd that work out for you?
Yeah, not the same.
Not the same. Okay. So we like this.
The end was 7, so.
Okay. Did anybody try something substantially larger than 10 to the 12?
I tried 10 to 50.
50. You got 1. Yeah.
Okay. I remember this case.
Yeah. So notice that there's actually a cap on how accurate we can get with this using real computers as opposed to the mythical computational genie that has an infinite number of places and can go infinitely fast, right? First of all, this requires a lot of computations. And second of all, we end up, at some point when we start doing really large values of n, we end up with problems or inaccuracies. Did anybody else try a large value of n? What did you try? Okay. I'm curious, what happens, try 10 to the 30th. Can we catch it in the act of getting a wrong answer?
Get
1. 10 to the 20th then.
1.
Still 1. Really?
1 with 10 to the 15.
What do you get with 10 to the 15?
1.
And 10 to the 12 still worked out. How about that?
I did like 10, 1 over 9 to 12. I mean 9.
Yeah.
And it was also
And it was 1.
It was 2.
No, when I do that, I get, when I do that, I get 2.78.
It's 10 to the 14.
It-
If you do 10 to the 14, you get 1. If you do 10 to the 13, and it's only 6 here, 6.
Wow! So we just sort of lucked out with our 10 to the 12 right here. Read me that again. 2.7606, blah, blah, blah. Yeah. Okay, so we don't like these facts. It should not be the case that as n gets larger, our answer gets worse. That's a bad computational thing. Everybody understands, do you understand that that's a function of the calculator and not a function of the actual math? But we would never necessarily know that, right? So if poor Euler had been working, instead of with hand calculations, if he had been working with one of these, he might never have discovered it. He actually would have, because he was, well, he was doing some proofs. So Euler does some poking around, and he comes up with a second way to compute this. And I'm going to give it to you now, but we're not going to prove it until February. So here it is. This is hand waving number 2. We're going to compute E as the sum from n equals 0 to infinity of 1 over n factorial. In other words, 1 plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, etc. And if you examine these terms here, you can see that they get, the numerator, the denominator gets very large very quickly. The next term here is going to be 4320. The next term after that is going to be about 360,000. So that we only need to go out to about n equals 20 to get an extremely accurate estimate for E And as I continue to add terms, it gets better and better. So this is a superior computation for E, even though conceptually we don't know quite where it comes from yet. Spoiler discovery. Okay, now with that in mind, let's talk about a famous limit. When we became interested in this limit right here, which you probably remember from last year. Do you remember the value? It's 1, yeah. But let's see why that is. Your calculator will tell you this. But what we're going to do is we're actually going to consider the quantity that's expressed right here. What is e to the h? Well, e to the h is going to be the limit as n goes to infinity of 1 plus h over n to the n minus 1, all of that over h. Now what I'm going to do is to consider this quantity as being all inside the limit, because this is the same as limit as n goes to infinity blah blah minus limit as n goes to infinity of 1, which is using the difference rule, and likewise I can do that with the quotient rule. And so let's take this quantity and expand it using our binomial theorem and see what we get. When I use the binomial theorem, what I get is 1 plus n choose 1 times h over n plus n choose 2 times h over n squared plus, all the way out, n choose n, h over n to the n power. Minus 1, of course, and all of that divided by h. Well, boom, boom, that cancels. And also, I have a factor of h in every single term here. And so I can cancel out one factor of h to get n choose 1 times 1 over n plus n choose 2 times h over n squared plus all the way out to n choose n times h to the n minus 1 over n to the n power. And so we're ready to take these limits. The problem that we have when we attempt to take these limits, however, is that it's not at all clear what's going to happen with these guys. Yeah, it's not at all clear what's going to happen with these guys. This is 1 over n because a factor of h cancels.
Oh, I see.
Yep. So in order to evaluate this, I'm now going to pull off my third and last, final, hand waving, and that is that I'm going to assert that I can exchange the order in which I take limits. This is not always the case. Limits cannot always be exchanged. They can only be exchanged for functions that are not simply continuous, but what we call uniformly continuous. And I'm just going to wave my hands and say, hey, this is a uniformly continuous function. And you're all going to go, uh-huh. And that means that I'm going to be able to exchange the limits right here. So this is a non-trivial step, and you're just going to have to trust me that it works. And so for the third time today, I really wish we could start with logs. But having exchanged these, now things become delightfully easy. What is the limit as h goes to 0 of all this quantity right here? One over n times n choose 1, right? Because every other term here goes to 0. Boom. what is n choose 1? It is the number of ways to choose one item out of a set of n. Well, what is that? 10. No, not even in factorial. I have n items. I have 8 people. 9 people. How many different ways can I choose one person? 10. That's right. So that our quantity is in fact just 1, and I get the limit as 1. Mm-hmm. Yes. Yeah, unfortunate that n's and h's are so similar and that my handwriting is so bad. Okay, you say, well, how does this famous limit help me? Because it gives us our last result for the day. We've been building up to this point. My claim is that the derivative of e to the x is in fact itself. And the proof, now that we've done the hard work, is really, really easy. Observe the right form, Caleb. We set it up using our limit definition, as we must. And now, we appeal to our exponential property. And we observe that we have a constant multiple sitting right there in the numerator. So out it comes. And we are left with this quantity right here. The quantity looks really familiar. What is its value? 1. Right there, this whole thing goes to 1. And I get e to the x times 1. Boop. Well, where does this leave us? The math was a little bit dubious at 3 different points. And so what I would like for you to do, rather than memorize these proofs, which I find to be, sketchy. I would like for you at this time to know this as a brute fact, which I think is how you approached it last year, right? And I would like for you to know the alternate way of computing E as a brute fact. We will prove it in February. And I would, of course, like for you to know your 3 properties of exponentials, but do not worry about the proof at this time, because again, I'm waiting. I would also like for you to know your 2 different forms for the number E. And if you have all of that, then you have what you need. Is that fair? So the one proof that you need to know is the derivative for e to the x, and that's pretty simple. See you tomorrow.